So far in the course, we've worked with y as a function of x, and we've found the derivative, so we've found dy dx. Sometimes we can write that as f dash of x, and we know that that's basically dy dx, or f dash of x is what's called the gradient function. It tells us the gradient of f of x at any point. So if we were to think of it in graph wise, there's my function of x, my x and y, and if I was interested in the gradient when x is equal to a, I simply substitute in f dash of x, so I do f dash of a is the gradient of f of x at x equals a. Now it's the gradient at x equals a, the gradient of the curve, which is also the gradient of the tangent to the curve, so it's the gradient of that as well. And the gradient is the rate of change of y with respect to WRT, so rate of change of y with respect to x. So that's what dy dx is. So when we're graphing functions of one variable, x, y depends on x, we only need two dimensions. If we had a function of two variables, x and y, so we'll go z is a function of x and y, so you're going to have z equals, and let's just use say 4 minus x squared minus y squared. So we've got z depending on not only x but also y. And it's pretty obvious that we're going to need three dimensions. Now just go back and revise. We've got x going there. Which way do we orientate our axes? Well, we use the right-hand method. So we point our fingers towards there, curl our fingers towards, so this will be my x, curl my fingers towards the y, so my fingers are pointing out that way, and I curl my fingers around towards the y, and then the thumb on my right hand will point straight up the page. So imagine x there, y going straight into the page, and z will go up the page. Okay, so there's my x, y and z. To try and get a bit of a handle on what this is going to look like, if we've got say x equals 0, y equals 0, and substitute in there, you'll get z equals 4. So 1, 2, 3, 4. So here, at this point here, x and y are both equal to 0, and z is going to be equal to 4. You could substitute in an infinite number of values, but I'm not going to do that. You can see that no matter what x and y values I take after that, even if they are negative, when you square a negative, you're going to get a positive. So z will always be less than 4. So if you like, this is like the pinnacle or the top of the graph of 4 minus x squared minus y squared. Every other x, y value I put in there, z value will be less than 4. So we don't get a curve when we sketch this function, we actually get a surface. Now this is in your notes, and the x-axis, now if we look at here, this z has got 4, 3 and 2, so it doesn't go all the way down to 0. My x values are going, so my x-axis, if that's 2 and then you go 1, 0, I haven't enough room on this to actually do the sketch, but my x-axis would be parallel to this line here, because it's 0, it would be parallel to that right down here somewhere. So there's my x. My y-axis, similar type of thing, would be parallel to this one here. Straight underneath, so there is my y. I'll have to do that over the top of that. So there's my y, and my z would be straight up And there's my z. So we've got x, y, and I'm trying to go through that 0, that's 0, so I try to get through that point there. But anyway, you can see what's going on. The x-axis is not there because that's when z is equal to 2. So it would be parallel to that 2 units down. The y would be parallel to this line here, 2 units down, because this is z equals 2, and my z would be my vertical there. So here is the point 0, 0, 4, and so you get a surface that looks like this. Now if you like, you can substitute in x equals negative 0.5, y would be equal to negative 0.8, and when you put those values into z equals 4 minus x squared minus y squared, when you square those two, you'll get a z value of around about 3.11, which corresponds to that point there. Okay, so that's graphing in 3 dimensions. Now we're going to further this in the next few videos and talk about partial derivatives, but that just gives you a bit of a rundown on graphing in 3D.